is New York City, Manhattan. In the center you have Rockefeller Center and the Sunken Plaza where the people go ice skating. I bet many of you know that or have been there. Let's do a little detour and think about our modern society we do in fact live in, and this is just to illustrate that fact. This is an image of a car, obviously, and all the parts that the car is made of which there are a lot, because a car is a pretty complex machine. And you can think about buildings in a similar way. Buildings are arguably maybe even more complex machines than cars. They have to provide a comfortable and safe interior environment, irrespective of the climate on the outside, whether it's hot or whether it's cold, whether it's raining or whether it's dry. And that may sound simple, but it's actually quite complicated at times, and they have to be safe, and they have to stand up, and they have to fulfill a program. So buildings are complex machines, and as our society becomes more computer dependent almost, buildings are also more and more computer driven compared to the building model in the past. That means that the planning process of buildings gets more and more complex. And I don't want to get into the details of this particular slide. This is just a graphic illustration of the involvement of various parties that are part of the design and the construction team. Namely the architect, the structural engineer, then there are the MEP engineers, mechanical, electrical, plumbing, there's geotechnical, there's landscaping, there are many other specialties possibly that become involved, like security, audiovisual. And all of that has to be integrated into one building. That's much more complicated than building a car, where everything is designed by one company, the car company. And therefore, often buildings don't work too well on day one because there were too many cooks spoiling the stew and nobody tested the whole building out. And then it takes a long time to get the building running as efficiently as it was designed to do so. So the green building community, they advocate for a rethinking of the traditional design process. So what we're showing here in those diagrams is like the traditional design process on top, where you have time is on the x-axis, where the bulk of the work, so the y-axis indicates the amount of work at any given time in the process. The bulk of the work occurs late in the design process, during the production of construction documents. And at that time, it's too late to make fundamental changes. It's too late to maybe incorporate a smart green building idea that somebody may have. So what the green building community is arguing for is to shift the burden, not to increase more work overall, but to shift some of that labor into the earlier parts of the design process. You see this hump on the lower slide of the graph here, so that all the parties can sit together in one room, meaning the architect and all the specialty engineers, and talk it over before fundamental decisions have been made, before it is too late, while it is still possible without a monetary or a schedule penalty to make changes. This is the way we believe to realize smart green buildings. And there's a tool out there, and Randy just alluded to it briefly, that is called the LEED rating system. So LEED stands for Leadership in Energy and Environmental Design. So this is a tool, a rating tool, a point system basically for building certification that is voluntary and that has been developed by the United States Green Building Council. But it can be used worldwide, and it is being used worldwide in China and the Middle East and in the US and everywhere. And this can be a great tool to give to the design team, or tell the design team, use this as a guideline, not as a straitjacket, but as a guideline to develop your design and incorporate green measures into your design. So basically the notion is, wouldn't it be great if for buildings we would have a label that tells you something: this building is energy efficient, this building is water efficient, similar to the labels we see on food: X calories, X gram of fat, X gram of carbohydrates, so that that we can be more knowledgeable about the buildings, because just looking at the building, you don't know. An inefficient building may look the same as an efficient building. And so LEED was started in 1999 with a pilot version, as far as I remember. And the mother of all the systems is here in red, the new construction system for new buildings. But it has since spawned a couple of children, the commercial interior system, a core and shell system, neighborhood development, we talked briefly about it earlier, existing buildings rating system. So it can basically cover every type of building anywhere in the world, and if used in a smart way, it can be a great one to use. They are all structured in a similar way that there are some credits, they call each measure kind of a credit. Some are mandatory, they're being called prerequisites, but the vast majority of them is optional. And you try to achieve certain credits, like for example, be 10% more energy efficient than an average building, save 20% water compared to an average building, things like that, measurable improvements. And if you collect enough points out of 100, you can get certified at 40, you can get silver at 60, you can get gold at 80, I believe. Or maybe I'm mixing it up right now, but you get the idea. It's like the more points you get, the higher you can climb on the ladder here from certified to a LEED Platinum building. And LEED has been quite a success, and the process is managed by a sister organization to the USGBC called the Green Building Certification Institute. And the way it works is that the design team, together with the owner, they submit a package of documentation to prove via calculations, via written narratives, via the drawings, via the specifications, that certain green measures have been achieved. And that is being reviewed by the GBCI, or rather they contract out with companies who review project for them, and we actually do that. Tomasetti does lead project review work for the GBCI. And then there's some back and forth, some additional stuff has to be submitted typically, clarifications have to be made, and ultimately you can get a nice little plaque that you can mount in your lobby or on your building facade if you're successful telling the public about your success and maybe reaping the public relations benefits from that as well. So the LEED rating system has risen sharply. The use of it has risen sharply in the last couple of years. More than 1 billion square feet commercial space certified. In 2010, I couldn't even find any more recent number. And it shows no sign of stopping. I mean, it may flatten out a little because of the bigger economy right now, but it's certainly not going away. So I took the liberty to look at, are there any LEED certified buildings in the Dominican Republic right now? There is a database on the GBCI website, and the answer is at this point no, but there are 3 projects in the pipeline, meaning they are registered but not yet certified. They're somewhere in the process. One is the one on the left. I'm sure you know, all of you know about this project, the Ana Kaona 27 building, which I understand is under construction right now, which seems to be a very exciting project. And I also took the liberty, or rather in the next slide, first of all, I wanted to briefly talk about what Randy had mentioned. There is a way for buildings to get LEED certified, but as a person, like myself or I think 200 people at Tomasetti, you can't get LEED certified, but you can get LEED accredited if you study for an exam and you take a test, which is now a 2-level kind of test. There's LEED Green Associate as the beginner level, as a credential for you as a design professional or engineer or contractor. And then there's the LEED Accredited Professional credential, which has a couple of specialties. And there are currently 162,000, more than that, LEED APs, as we call them, LEED Accredited Professionals throughout the world. And I also took the liberty, as I just said, to check how many of them are in the Dominican Republic, and there are 13. And I wanted to ask, is any one of those 13 in the room here? Raise your hand. There's one there. Anyone else? Well, that's great. I hope you're doing a lot of great work going forward, greening the city of Santo Domingo in the country. Thanks for coming. So that's about LEED, but it's important to remember LEED is a tool. LEED is not the goal in itself. LEED is a tool to get to a bigger goal, which is creating a green building. Okay, and to do that, I wanted to do a little detour here and talk about things we have maybe forgotten in the past, in the post-war years, when we became over-reliant on mechanical systems to create an indoor climate in our building that could just ignore what was going on the outside of the building, meaning that we got into the habit of building the same type of office building with a curtain wall envelope in Texas as in Alaska, in a cold climate versus a very hot climate, and we would either heat the building or we would cool the building to create an indoor environment that was comfortable, and that was relatively painless for a long time because the energy to do that was cheap. Well, that is changing now. Energy is becoming more expensive, and it is becoming more painful to waste energy, as of course you shouldn't do. So now we're getting back to learning principles from nature or from old buildings that we sort of made the mistake to get away from because it was too painless to do it. And I want to go through a couple of slides that are taken from a study we did for this building here, which is in Saudi Arabia, in Riyadh, where we worked for the architect FX Powell in New York to help them develop a sustainability strategy. And you will quickly get the point of what I'm talking about here. So this is a museum that is right in the middle there of this King Abdullah Financial Center in Riyadh. And what we've done there as a sustainability consultant was to look at a couple of strategies, let's say, and see how are they applicable in nature, how were they relevant in the last century, maybe 200 years ago, 300 years ago, and how are they relevant now? So there's first of all shading. We can have roof canopies, we can have expansive roof overhangs to shade our building to protect ourselves from the heat. And Saudi Arabia is certainly a heat-dominated climate, so the objective typically is we try to keep the heat out of the building, which would be similar to the case here in Santo Domingo for the most part. There is vertical shading. A cactus has ribs so they can shade each other as the sun revolves around the sky. There are vertical shading elements, blinds, shutters, and things like that are part of a traditional architecture in hot climates, certainly. And maybe it's time to bring them back into modern buildings as well, like here in the master city development in the Emirates. There's of course reflective surfaces. We all know white reflects the heat while a dark surface absorbs the heat. So traditionally in Middle Eastern countries as well as in countries like Greece, there are many more white buildings than there are in the Northern Hemisphere. There is natural ventilation. Again, we became to expect, or we're living almost in an era, in the US at least, of total reliance on mechanically ventilated buildings, and the notion of taking advantage of the natural convection of air as warm air rises to the top, that could induce ventilation, like it does in a termite mound, like it does in this building in Zaire on the right side, has gotten away from us, and it's time to bring it back. Let's bring back natural ventilation in our modern buildings. We can take advantage of the wind. We can funnel the wind into our buildings, like here in the middle. You see so-called wind catchers on top of buildings that bring in the wind and through this kind of chimney there, thereby dragging the hot and used air out of the building interior. There's evaporative cooling, meaning that, like this bird does, if it opens its mouth, there's a liquid, and as that evaporates, it cools. And that's exactly what we humans do, by the way, when we sweat, and there's a wind blowing, there's a breeze blowing over our sweat, and it evaporates, it cools us. That's the purpose of sweating, ultimately. A dog has to stick his tongue out, or her tongue out, in order to do the same thing. And if you have strategically located bodies of water or water surfaces close to the building, you can significantly cool down your building. There's taking advantage of the mass of buildings. As over the course of the day the sun heats up the building, if we have massive walls like masonry, like concrete, they can store the heat and release it later at night, preventing buildings from overheating during the day. And there's, of course, a multitude of ways to bring in daylight into the building, and it has been proven that people respond positively to daylight. Nobody wants to be devoid of it and sit in a windowless room, as is sometimes the place. So we should get back to learning from nature, or be more open to learn from nature, I believe, and try to integrate those fundamental concepts which are basically rooted in elementary physics, and use them in order to create buildings that are smart and efficient. And one basic tenet for that is, before you even set out to design a building, think about the building massing and the orientation that the building should have. That is crucially important for efficiency, and once you got it wrong, there's no way to fix it. So we propose that you should study the local climate, the local solar pattern, the environment of your building, in order to see to what extent is your building going to be shaded, and to what extent do you want to take advantage of that or avoid that. To what extent do we want to bring the sun in or keep the sun out? So there are, as I said earlier, a bunch of heat-dominated places, like the desert, like the Caribbean here, where I understand most buildings don't have a heating system. So generally, you want to protect yourself from the heat on the outside. Then there are places like, let's say, Alaska or Greenland, where the reverse is true. You want to orient your building in a way to bring in the heat, open up solar exposure on the southern side of a building, open it up and bring the air in, bring the solar radiation in. And then there are temperate climates like New York or Northern Europe or the middle of Europe, where it gets a bit more complicated, because both is true. In the summer you want to keep the sun out, and in the winter you want the sun in. And that presents certain challenges, as how should I design the geometry for my building? What does it mean for exterior shading and the orientation? And thankfully now we have advanced modeling tools like those screenshots here that we can use to become smarter about it. So here is the similar study we did for the museum in Riyadh, where we discovered through modeling that even though the building is surrounded by a lot of other buildings, there was still a very substantial thermal heat gain, solar heat gain, that we proposed to the architect to protect the building against by adding exterior shading elements. And then there's also the aspect not only of protecting or inviting in the heat, but what about renewable energy? What about hot water? Solar hot water or solar power generation, like photovoltaic cells on the facade of your building or on the roof of your building. Well, in order to make that as efficiently as you can, you have to study the solar potential of your rooftop with a similar computer study like this one here, where this is a high school on the Upper West Side of Manhattan, where we performed this study for 2 photovoltaic arrays And we try to locate them in a way that the shading of those surfaces was minimized over the course of the year, not on any given day, but over the course of the year in aggregate. So then there's, back to what we do as architects and as structural engineers, let's talk a little bit about materials, efficient material use. Dan talked a bit about structural efficiency, which we basically measure in how much steel, how much concrete do we use per square foot of building, of floor area. That's an indicator of the efficiency. And we are certainly advocating to never use more than you have to use in order to get the job done in a safe way. Never compromising safety, obviously, structural stability, but don't use more than you have to deliver a safe building. And with that, in my opinion, and speaking as an architect, also comes a responsibility that lies with our profession not to design buildings that are unnecessarily bigger than they have to be, to have a program that is commensurate with the building size. And if you ask my personal opinion, nobody needs a house that is 50,000 square foot large and has 20 bathrooms, even if you can afford it. I mean, even if you're very rich, you can only use one bathroom at a time. So limited to a reasonable number. Okay, same with the kitchens and everything. And so have the buildings a reasonable size, have them with efficient structural load paths, don't use more than you have to. And I'm sometimes using this slide to illustrate that point that I just made. So everybody knows the building on the right side is the Olympic Stadium 2008 in Beijing by Herzog Dümmeron. The building on the left side is also an Olympic Stadium in 1972 by Frei Otto and Günter Behnisch in Munich, Germany. And they're both stunning pieces of architecture. I absolutely admit that. I love the bird's nest, but there is a penalty that was paid because this is an order of magnitude more steel that was necessary to make the aesthetic of the bird's nest possible. These are all steel beams, this lattice work, versus the stadium in Munich is an efficient tensile structure with steel cables. And so I think this discussion has to be allowed. We have to be allowed to challenge architects on their designs if they force structural engineers to become less efficient than they could otherwise be. And that leads me to a sort of a pretty recent development in our company and throughout the industry, which is the focus on so-called embodied energy and embodied carbon. And I'm going to take a minute to talk about, first of all, to explain what I mean by those terms. When I talk about operational energy, I'm sure everybody understands what that is. That is the energy that we use to run our buildings. Again, lighting, heating, ventilation, air conditioning, equipment loads. That's basically it. Pumps for water. And all of that energy, the large majority in the US and probably in the Dominican Republic as well, comes from power plants that are burning what we call dirty fuels, coal or natural gas. I mean, fuels that are not clean, that are not renewable, that have a greenhouse gas emissions impact, which we want to bring down again. And when we talk about the embodied energy, that is all the energy that we have to use before we even move into the building. All the energy used for extraction of raw materials, shipping the raw materials to the manufacturing sites, refining them, manufacturing them into building materials, shipping them to the site, and the whole sequence of construction activities. So if you picture those processes, you can picture a lot of energy being used for transportation, and picture a steel mill, picture a concrete plant. These are very energy intensive operations, and that energy similarly comes from coal-fired power plants or gas-fired power plants. So there's another greenhouse gas emissions impact on top of the operational one, which illustrates even more that the imperative for our industry, for the design and construction industry to bring down carbon emissions is very large. Here's a statistic from the Department of Energy, again for the US, that says on the left side here, you see this is operational energy. 40% of the total energy used in the US, used in buildings. But this does not include the embodied energy, which is somewhere, I don't know how big this slice should be here, but it's somewhere straddling the boundary between the industrial and the transportation energy sectors. And the chart on the right is a case study from MIT that illustrates that the embodied energy, which is the horizontal flat bar, black bar, over the life of the building here, assumed to be 90 years, it takes for a highly efficient building like the one indicated by the yellow bar, 60 years to use as much energy operating the building than was used on day one of the building for building it. So there is a strong case to be made to focus on embodied energy, and this slide here further illustrates that this is very important to us as a structural engineering firm, because according to this case study, a whole 57% of the total embodied carbon impact that in turn is linked to the embodied energy is made up by the structure: steel, tiles, meaning the foundation, and the concrete works. So we are in a position to lead our industry to try to scale it back, and that's what we're trying to do. And we have developed, and I want to show you a brief movie here, a pretty exciting tool, in my opinion, in-house, that uses a parametric tool here to quickly and early in the design process assess the carbon impacts relative to fundamental design decisions. So we have an interactive 3D model here in the center, and we can, with those little sliders on the right side, we can manipulate design parameters like the bay size, meaning the distance from column to column, the floor to floor height, the building footprint, while keeping the total building size constant, and the foundation layout, and get instantaneous feedback on the left side by those charts, broken down for steel and concrete, of embodied energy per square meter, embodied carbon per square meter, and materials used per square meter. What Dan talked earlier, structural efficiency, structural material use per square meter. So I'll show you how that movie works. So this is a live movie snapshot from a screen where one of our little tech modelers showed you in real time how that works. So now we're switching from steel to concrete. We're changing the bay size. You see the amount of columns changes, and the one thing we have learned is that the smaller bay size is better because the size of the floor framing is going down more so than the material gain for the column goes up, so to speak. And you see on the left side the bars going up and down for those indicators, and this is great in my opinion because we as designers, we don't have an intuitive sense for what are carbon efficient or inefficient design decisions. We have developed this tool because we want to learn it. We want to learn that maybe certain ways of designing structures or buildings are more carbon efficient than others. And this is just starting in our industry, and I think it's an important part of the future discussion in our industry. We can change the amount of recycled steel we have here. We can change the amount of cement replacement we have, like fly ash, like slag, and so on. So I'm looking forward to using these tools. This is a generic hypothetical building. This is not a real building. This is right now an in-development tool, but I'm looking forward to using it on real projects. And I'm going to close again with a thought on existing buildings. I started the discussion in my previous part, and let's look at some existing building projects and how we have helped our clients to green them. So this is just a smattering of high-rises in New York City where we have helped one big real estate company there, Vornado, to certify them under the LEED for existing building operations and maintenance rating system, and you see the buildings run from old stone buildings, brick buildings, probably from the 1920s, maybe the 1910s, to post-war buildings, the typical glass curtain wall buildings. And it was possible for all of them to certify them under a LEED by being smart, by having a smart team, and by having an owner who is committed to make it happen. It's not an easy process, but it is certainly possible and worthwhile. Here's one example where we were involved as the curtain wall consultant. This is a building right around the corner from our office in New York, right on Madison Square Park, from 1909, more than 100 years old. And after we were done with everything, after the team was done with everything, the building looked like this. Well, it looks the same, which is to illustrate the fact that you don't see it. You know, the green building improvements are not apparent to the naked eye. They happen in the basement. They happen in the boiler room. They happen on the rooftop with the cooling towers and the air handling units. They happen in the bathrooms and the kitchens and with the ventilation system. So a lot of the green building improvements are somewhat not very glamorous, but still provide you with a lot of bang for the buck, so to speak. Here's a photo of the same building of the interior courtyard, where they introduced little green roof gardens. And here's one that Dan will talk more about it in a moment, I believe, the Taipei 101 building. We were the structural engineer in 2002 or so. It was completed in 2004, I believe. And at that time, sustainability was probably not on the agenda. And a couple of years later, the owners of the building thought, well, wouldn't it be great to certify that building? And they did, and you said on the day they did, they had the windows illuminated like that to read LEED. And this is now a LEED Platinum certified building, the tallest and the largest LEED certified building in the world. Incredible success. But not only that, look at the numbers at the bottom. The owner saves $1.2 million a year in operating costs for the building. So even if you don't believe in all this sustainability hocus pocus and the tree hugging element of our profession, the dollars certainly speak very loudly if you're a building owner and you are interested in improving the bottom line on your bank account. Another very famous building has done the same thing recently in New York City with the help of President Clinton's climate initiative. And it's now also a LEED E-bomb, existing building, a certified building. We were not involved with that effort, but let me point out some of the numbers there on the right side as well. 38% energy savings compared to what it was before. $4.4 million energy savings per year. Very substantial savings. One measure they did, which I think is really great, I want to point out is, you see the window, the little window vignette there on the bottom. So they brought in Serious Windows, which is a high-performance window manufacturer, and they refurbished each building in the building, 6,500 windows, put them, they converted one floor of the Empire State Building to a refurbishment factory. They dismantled the windows and integrated a third layer, not glass, but a film, and dramatically increasing the energy efficiency, the thermal resistance value of the windows, and making this possible. And with that, I'll hand it over to Dan. Thank you.
Okay. Thank you. Hello again. I wanted to talk a little bit about another type of construction. I'm going to try to do this a little quickly because I have two other things I want to do before we take the break. It's called top-down construction. Some of you may be familiar with this, and it's a method of construction that we've used on a few projects, and it has certain advantages. Top-down basically means you build the building, the superstructure, and you build the below the ground at the same time. So the advantages are that you don't normally, when you build a basement, if you go down too far, you can't go down the full depth of the basement without putting some sort of anchors or tiebacks in the wall, because otherwise the soil will just will collapse the basement wall. So what happens in top-down construction is you start building, well, let me go back to this one. You start building from the ground, and then you excavate one floor, and then you put the slab down below, and then you excavate under that. You have to have an opening so that equipment can get down. You excavate under that slab, you pour the slab, you excavate under the next one, you pour that. So what happens is, as you put these slabs in below the ground, they brace the walls so the walls don't collapse, which is what happens in the final structure of the building anyway. And just keep that in mind, because when I talk about the World Trade Center, that comes into play as far as how these walls, basement walls, are braced. This is a project in Washington, D.C. It was a hotel project, and the area in red was the site of the building. And you could see there were buildings all around. It's an existing site. The yellow are the streets. They were filled with all types of utilities, so there was really no way to put staging area, to put equipment, and so on. So it was important to, and also a lot of times in the walls you'll put tiebacks through the soil, and they'll anchor into the soil or into rock. There was no way to do that because there were utilities in the streets, and you'd have a problem. So the top-down construction was utilized. And I won't go through all the detail here, but essentially it's a slurry wall type construction, and some of you are familiar with that. You dig with a clam bucket type, you dig a hole in the ground and you go all the way down the yellow area. Up at the top there, you see in the red, that's the clam bucket. It digs down, you fill it with some sort of a slurry, clay type slurry, so the soil doesn't come into the hole. And then you put the reinforcing cage in, and then you put concrete in. You go from the bottom up, so it displaces the clay mixture that's in there and fills with concrete. So you can actually build a concrete wall in the ground, and it's called a slurry wall. And a similar type of construction for the columns. Caissons were put in, and the columns were put in afterwards. And this shows the progress of construction, where they're digging actually underneath the floor that's already been placed. And in the right, you see that little diagram. You can't really dig the full depth of the next basement floor next to the wall, because the wall could collapse because of the soil pressure. So you have to have that little slope in there. So that's the way the excavation is done until the slabs are placed. So it's a step by step, floor by floor, one at a time. Meanwhile, the building is being constructed above the ground. Just another, you see where these slabs, they're excavated underneath. And the other interesting part of this is at the ground level, those red lines that go across, there are no columns underneath because it's a ballroom and needs to have open space. So, and this is a section here, those blue things above the pink, those are the transfer girders that go across, and they're pretty deep. You could see how deep they are. And the final building, now it's will be completed in 2014, and it's 93,000 square meter total. 40% of the building is underground, and the 60% is above. And in Washington, D.C., if you're not familiar with that, there is a height limitation. So in order for the hotel to get the ballrooms and everything that they needed in the hotel, and to get the square footage of area, they couldn't go up above a certain height, and that's the height of the U.S. Capitol. You're not allowed to build higher than that. So the only thing they could do was to go down. So that's why they have so many basements in the building. I'm going to just not spend too much time on this either. Building information modeling, and a lot of you are already doing this, or BIM as it's called. It's really what's being done on every project that we do anyway. You know, the way I look at it is, and it's not CAD. You know, I look at what CAD was to manual drafting, BIM is to CAD. You know, instead of drawing lines, you're drawing with objects. So each line on that drawing actually has properties on the left. So if it's a beam or a column, it has all these properties in it, all the dimensions, the weight, the volume, and so on. And you can do a lot of different things. You can visualize, you know, it has different benefits. This is a project on the right. You can see there were 3 towers over a railroad yard. So by using BIM and the animation program, we were able to show, you know, what the impact was. We discussed with the owner, the architect, and the fact that we were avoiding the railroad tracks with the columns, which is a good thing. Very complicated structures can be modeled a lot easier with BIM. Coordination, big advantage there. You can, as long as all the team members are using BIM, and there are issues with that because there are different platforms for building information modeling, and they don't all talk to each other. We have in-house people that have designed the interoperability program, so we can talk from one to the other, but that's an issue. But if all the team members are using BIM, using the same model, you can put the architectural information, the structural information, the mechanical, electrical, plumbing, fire protection, and so on, everything into place. And one of the advantages also of BIM and the modeling is you can do what we call clash detection. You can determine if something is interfering. And here you can see, in this case, we didn't really do this, but I just showed the example here. The beam going through the escalator, okay? So make it very difficult for the escalator to work. So this is something that is better to find it before you actually build it. So that has that advantages. And you can also generate all kinds of models. On the left says core studies. This is a project, some preliminary work that we did for a project in Dubai. It's called, well, it's now called the Lagoons, but at the time it was called Candles in the Wind, because these towers were supposed to look like candles, like the flame of a candle. And all we had initially was the 4 little diagrams on the left, with the architect had done some studies of core. So we wanted to see how can we fit a structure in this shape. And we were able to formulate the shape, and actually we did that by combining a whole bunch of things. We did a cylinder, and then a twisted cylinder, and then a cone, and so on. And we combined the first 4 models to get the 5th one. And this is something we did like in about a week or so. We were able to do this and show the architect that, in fact, we were able to have a core that went up to the whole building. You can, there are different modules and the different packages where you can actually detail the connections. It'll show you exactly how many bolts, exactly the size of the welds. It'll show you the plates and everything, which is you know, we've actually used that on some of the stadiums that we've done, and it saves a lot of time by doing that. The contractor, sometimes he'll take the model and do it. We've actually done it in the design phase and actually detailed some connections for complicated projects. You can make shop drawings right out of the BIM model. And not only that, you can use the same model, send it to the fabrication shop, and if the fabricator has computer numerically controlled CNC equipment, you can actually fabricate the pieces from the model. You can punch the holes, you can coat the beams, you can do all kinds of things. And you can even print out the part number. And it has a lot of benefits. On the right, you see something very complex structurally, a lot of members all framing in at different angles and everything. And you know, if you give a contractor a two-dimensional drawing to try to show that, and you could put sections and all kinds of things, it's still very difficult to visualize. Whereas you give a model, and it's very clear how those members come in and connect. You can define the scope of the job a lot better. Down at the bottom, you could see a lot of different members. Nothing really gets lost. And you can save a lot of time because you can actually start detailing the building. Contractor can start doing it before you actually finish the design, you know, just using this model. So it works very, very well. I mean, if you're not using it, you should be and you will be. Well, this is just another model. It shows how you can take a model and kind of fly through it and shows everything. So Taipei 101 was completed, as Wolfgang says, it was completed in 2004. It's a 101-story building. That's the name, Taipei 101. 508 meters, and at the time, it was the world's tallest building. It's a combination of steel and concrete, primarily steel in the core, the moment frame, the outriggers, and we have super columns on the outside that the outriggers connect to that are really composite. They're concrete and steel. The building also has a damper at the top, and I'll talk a little bit about that. So here we see the lateral load resisting system is essentially, again, it's the braced core in the middle, the yellow, and the outriggers, those trusses that come out, okay? A lot of them, there's 8 of them in this building. Try to control, it's a pretty tall building, try to control the drift. And here's the analysis model and the construction, and that's actually one of the, down at the right, is one of the super columns, as we call it. These are there's 8 columns, there's 2 on each face that the outriggers connect to. So these are really heavy, massive columns, and they're composite. You can see here, same picture on the right there. But on the left, on the upper left, see that man standing next to it. That gives you an idea how big those columns are. On the right, you see a hole in the middle. That's to put a reinforcing cage that you can see at the bottom, some rebar that goes down. It's a circular cage. Those little holes around there that go through the plates, they're to place rebar, individual rebars, and you can see those at the bottom as well. Those ties across, so the steel plates, which are, by the way, 61 millimeters thick, they don't pop out when you put the concrete due to the pressure. So it's a pretty large undertaking here. You see the corners of the building are like stair steps. And what was interesting is we determined in the wind tunnel testing that was done that this actually was a lot more efficient than having a square corner or a round corner, even a chamfered corner, straight angle corner. By putting the steps in, we were actually able to reduce that vortex shedding that I talked about earlier in the building, and it had a very significant reduction in that, which obviously helps in the crosswind direction and the acceleration of the building. Now, the building, even based on the wind tunnel test, the building actually worked. The accelerations were within the China code, but they were worried, you know, you're in a typhoon area, so you're worried about typhoons, and even though it still looked like it would be okay, we investigated putting a tuned mass damper at the top of the building, and that actually reduced, I just want to give you the right figure here, the milli-Gs on the building. With the typhoons, the China code actually says 25 milli-Gs was the maximum. Without the damper, we were actually at 19.3 milli-Gs. So we were actually under the limit, but when you put the tuned mass damper in, it reduced it by 40%, went down to 11.6, which was a very significant improvement. So the owner said, and it's 660 tons, 5.5 meters in diameter, it's $4 million, and it could move up to 1.5 meters in each direction. And the way it works, you can see here, as it's a pendulum. It's called a pendulum damper because, as you can see, it acts like a pendulum. And those red and white shock absorbers at the bottom are viscous dampers. So what happens is, as the pendulum swings, those dampers at the bottom, the shock absorbers, will, like your car, okay, and they absorb energy and they stabilize the building. And actually, I took this picture when I was there a few years ago, and they actually made this a tourist attraction. When you go in the building from the upper levels, you can actually look down and see this damper, and they call it Damper Baby is the name, and they have this big sign on the wall, and birth date was 2004, that's when the building was completed. Birthplace, Taipei 101, has the height and weight. Favorite extracurricular, music, I guess, swing. Favorite weather, typhoon and earthquake. Mission to protect Taipei 101. So it's kind of cute. They made and it's literally a tourist attraction. Now, what happened was, in May of 2008, there was an earthquake in Sichuan, which is about 1,800 kilometers away, and there were people there. Somebody actually filmed the damper moving in the earthquake, and you could see it's a little shaky, but you could actually see the moving. See the pistons down at the bottom, at the lower left and the lower right. Those are the pistons opening and closing, and you could hear people talking. They're not screaming and running out of the building, but it's they actually got a chance to see this thing in motion. It's about a couple of minutes, and those are the cables that it actually hangs from the top. I just want to show a little bit more because you could see people all around watching this. There's people taking pictures. And see up here, there's a lot of people still in the building. So it was working. Otherwise, they would have ran out of the building. See? Look at all those people. Very happy. Okay. This is the last one before we take a break. Shanghai Tower, this building is under construction in Shanghai. And it's an interesting building. It has a twist to it. Its estimated completion is 2014, 632 meters, 124 stories. And this is the way the building stacks up. It has every 16, 17 floors, there's what they call a refuge level. It's used as a mechanical room, and it's also a refuge level that they use for emergencies, fires, what have you. And that's a code requirement. So at each of those MEP and refuge levels, we took the advantage to put some outriggers in. Now the interesting thing is, it may be hard to see here, but the structure is actually circular. It goes all the way up the building. And that twist and the varying dimension of the facade is actually hung from the structure. So the structure itself doesn't twist. It's the exterior that does that. And the twist is a 120-degree twist. It's about a third of the full revolution from the bottom to the top. And actually, this was determined in the wind tunnel test that this was the optimum twist angle. And believe it or not, the twist and the shape of the building actually reduces tremendously the effect of vortex shedding on this. So typical floor is a concrete core in red. It's 30 meters by 30 meters. Has steel deck and concrete for the floors, steel beams, and the super columns are those blue ones. There's two on each face, like Taipei 101, similar. And this is at those refuge floors where, in addition to the floor framing and the super columns and everything, we have these outrigger trusses that go across to the super columns. And that green circle in there, that's really the outline of the structure. And the other stuff around it is the facade of the building that does all the twisting. So now the green is actually, we call a belt truss. They're very deep steel trusses, and they're doubled. There's two of them right next to each other. And those trusses, in addition to the lateral framing, the outriggers and all that stuff that's for the lateral loads, in addition to all that, these double belt trusses, we call them, because it's like a belt, with the super columns actually gives an added type of resistance, and we call it, well, this is the foundation, call that a mega frame. So this is the entire lateral load resisting system. You got the red core coming down, which takes most of the load, actually. You have those outriggers, the blues that go in there, then you have the green, the belt trusses, and those pink trusses coming out. Those cantilever out to pick up the facade, that thing. So everything, the whole facade is really hung from the structure. And these double belt trusses now, with the super columns, act as we call it a mega frame, because it's a gigantic frame that also has some capacity for earthquake lateral loads. And it's, in a way, it's a second line of defense. Not only that, the Chinese code requires, and most of the US codes do, when you're using certain types of seismic systems, you have to have a dual, called a dual system, two different ways to take the load. And that mega frame takes 25% of the load. These are the steel connections. The right, you see the outrigger connected to the super columns, have these steel shapes in them to make the connections easy. Wind tunnel test was done. As I said, we studied different twist angles, 120 degrees. By doing that, the 120 degrees actually reduced the wind load 60% compared to a square building, which is pretty significant. The acceleration criteria met the code without the tuned mass damper. Right now, the plan is to put a tuned mass damper in, which will reduce accelerations by 40%. This would be the tuned mass damper in that building. It's similar to the Taipei 101, except you see what it is. The damper itself is hung from a frame, which is hung from the floor. So you have the damper, which sways, on the frame, which sways, and that's connected. And the advantage of this is actually you get the same effect as of a longer pendulum. So instead of having to go up another floor to put a longer cable to support the damper, okay, you can actually get the same effect by doing this. You basically add the hanger lengths of the bottom, the ones that connect the damper and the ones that connect the frame. So it's another idea for a pendulum. It's called a folded pendulum, but it takes up less space than the other one. 1,100 tons, so pretty hefty. And this is the last one I have here. This is it's a video through the building, but you see that the facade is actually away from the structure. And as you go up, you can see the circular structure is actually inside, and the facade is varying. It's twisting and coming around. So I think that's it. Yep, okay. That's it. Okay, thank you.